Hi everyone, and welcome back to another instance of Math Research Live with me, Charlotte Aten. Thanks for joining me again. Unfortunately I wasn't able to be doing this last week, as it turned out. I got very close, but I hadn't quite gotten my equipment set up. I was having some internet connectivity issues, but those have been resolved, so hopefully you are in fact seeing me right now. And it's really great to be back. As you can see, I'm in a new place that I was not before. You can see the lighting's not the best, but you can see some of my plants behind me. Maybe if the sun goes down a little bit, you'll be able to see more. It feels really nice to be able to be sitting here talking to you about math instead of driving and lifting lots of heavy things in the hot sun all day long, which is what I've been doing basically for the last 2 weeks. So it's really nice to now be able to start to get back to normal a little bit. And so I appreciate you sticking with me through that unexpected hiatus. Math unboxing stream. I'm going to have some brand new mathematics to open up for you, and you can you can watch as I open up a random assortment of theorems and propositions. I even have some unopened collections of porisms from back in the day when people used to prove those. Porisms are just like geometric propositions, I guess. It's just I actually do, believe it or not, I actually do need to go through many very heavy boxes of papers and notebooks and things from before I went basically 100% digital. And one of these years I will do that, and maybe at that point I'll pull out some of the more interesting stuff and show you, my old like Algebra 2 homework or something like that, and be like, this is when I was learning about Galois theory and that type of thing. That is actually a good idea, thank you. Today I thought that I would talk about the division by zero project that I had again, because I keep thinking that I was close to just describing an interesting construction that I had never really thought of it this way before, and so I wanted to just take a look at that live, and hopefully I'll be able to figure something out about it. And as always, just feel free to ask whatever questions, and we'll check it out. It'll be cool. So let's see. If you'll remember, actually I have the paper here as well. If you'll remember, I had the beginnings of a paper started where I was working on introducing the notion of free algebras and presentations of algebras in the sense of universal algebra by way of this construction of a system that I called the apportional numbers, where I guess it's debatable what you want to consider being like division by zero, but this system has numbers that we're meant to think of as things like 1 over 0 or 3/4 over 0, and maybe things like 1 over 0 over 0, and so on and so forth. The typesetting here is a little ugly, but you get the idea. So that was the idea. And my presentation of this, no pun intended, I guess, when I was, in my late teens, early 20s, whenever I first wrote a thing about this, my presentation of this was actually not so succinct. And so a big part of the previous stream that I had done on this was actually figuring out how to present this in a way that was understandable, or that was more succinct, or whatever. It was perfectly understandable before. It was just very long-winded and tedious because I was less mathematically sophisticated, and so I wasn't, I was doing everything in a way that's I would now consider to be too careful and too many, checkings of like little steps that are obvious to me now, and that sort of thing. So last time I settled on what I thought was a pretty nice treatment of this, and so I thought about this collection of apportional numbers being like pairs, where the first one was a rational number, like a fraction, and like a usual fraction, and the second one was a natural number, like 0, 1, 2, 3, whatever, and that like represented some rational number over divided by 0 repeatedly some number of times. Yeah. So that's something that we had there, and then the idea was I need to tell you how to multiply two of these things together if I'm going to have some notion of multiplication. And so I had a much less succinct way of expressing this before, but I realized last time that I could just say, well, if neither of these numerators are 0, then for these rational numbers, then the product should just be their product over 0 sub the sum of these two things. And if one of them is 0 over some number of times being divided by 0, well, then you can really just treat that as like 1 over 0 sub n minus 1 or m minus 1 or whatever the case is. And so it was actually pretty succinct to do it this way. And so that's kind of where we had gotten to, and like the goal, as I had mentioned, was that I wanted to talk about free algebras and presentations of algebras, which I think I did mention at least a little bit. But I wanted to think more about like what this operation is really saying, because if you look at it, there's actually not too much. There's not really too much that has to do with the specifics of the rationals or the natural numbers here. And so I kind of wanted to mess around with what it would look like, or what is sort of the general situation where we have two algebraic systems and we can make something like this. So I wanted to think about that because I think that might help me to understand sort of what I'm really doing in some sense. And it might be that actually what I have is something that is some kind of universal construction, or something that I can express as a categorical kind of construction. Oh, hello. Yeah, thanks for joining the stream. Yeah, so all right. Oh yeah, and so actually, speaking of my partner just hopped on. Speaking of my partner, so they made this really awesome donut emoji, like sticker thing here, and let me see, where is it? And so it's donut 3. So if you would like to experience the donut emote, be sure to make use of that. Because yeah, it's really fun, and we may have other donuts with other numbers of holes in the future as well. You can't really see it super well, but there's like really cool little like sprinkles and stuff on it. It's very nice. There's a high resolution one available somewhere as well online. Okay, so let me think about what I actually needed to do this construction. So basically I said something like, so maybe I have some algebraic system that, am I not over far enough? Let me see here. So basically, no, I'll just do this. Okay. So basically I have some kind of algebraic system A, and it has a single binary operation, which maybe I'll just call asterisk, and maybe I'm debating. No, this is fine. Okay, and it's going to have some constant, which maybe I'll call 0. I'll call 0a. And so the idea is this is the thing that in my specific case was the rational numbers with the usual multiplication, and this is just the number 0. So I had something like that, and then I had another system that was another algebraic structure that was some b, and maybe I'll do a different operation. Well, I don't know. Maybe I'll call this circled plus. Why not? And there's something that's like 0 in b, and well, yeah, no, I do want that. And so the idea was that, yeah, thanks for the question. Yeah, I mean, I find it rewarding. I mean, I try to take, as far as the reputable part of it, I mean, of course, I try to take the status like hierarchy kind of games, with a grain of salt, because I really am into, doing mathematics itself, and, there's a certain amount that you have to focus on, rankings and career, prestige and all that kind of thing so that you can survive. But, it's I really do enjoy doing math more than, flexing on other people about how fancy I am or that sort of thing. So, I try not to think about that aspect too much. I mean, really my favorite part is doing the math. It's just that, publishing in a journal is something that you've got to do both, job-wise and also to, get it out there for other people to see. I mean, who knows, maybe as time goes on, more things like, archive and stuff online will start to overtake the traditional systems a little bit. But yeah, I mean, the most rewarding part for me is definitely doing the mathematics and sharing it with people, however that may be. So yeah, I mean, overall I would say definitely quite rewarding. Yeah, it's I mean, I still, the archive is great, definitely. I still, think that there's some progress that can be made with respect to, not having things be so centralized, and like, of course, Cornell University is certainly a traditional center of institutional power, and so forth. But yeah, archive. It's like archive, like the Greek letter, chi. Oh, and I missed the skull. Yeah, see, here's another thing. Here's another complaint about the archive, is the skull and crossbones, the little icon for when you save it into your bookmarks, is gone. They've decided to rebrand, and it's some like aggressive looking like X kind of thing or something. I don't even know. And like it's like spiky. Yeah, it's like an X. But it used to be, it's some like spiky thing like that they did it like stylized, and it's like a fancy X, But it used to be like a skull and crossbones. Like it was, I don't know that anyone ever considered it to be like piracy or anything, but it was like, I think it was a little more underground back in the 90s and stuff, and like they finally got rid of the skull and crossbones, and I was disappointed about that. But yeah. Oh yeah, because it's archive, because it's the letter chi, because it's like, you use Greek letters and, in math and so forth. Yeah. Yeah. Yeah, I'm a mathematician, so I know the Greek alphabet, but I don't really know how to speak Greek, and so, that's how it goes. But yeah, so I had one system that was like my rational numbers, and then I had another system that was like the natural numbers with the usual addition, and this was also like the number 0 in this case. And what I ended up saying basically was that I wanted to define a new system whose numbers, were pairs of things, So I wanted to look at a multiplication rule on, pairs of things from here. Well, maybe subject to some equivalence relation. And so I guess that equivalence relation, I called it tilde before. Maybe I'll do that again. So I was saying that, like, maybe A1, or well, what letters did I use actually before? Why don't I just use the same letters? AM and BN. So I said that that's easier than using indices anyway. So, oh, now I did A sub M. That's also not what I wanted. So AM. So I said that I had a new operation I wanted to. Oh, I wanted to define this relation first. So AM and BN are related to each other. Well, there's only one interesting relation, or one interesting aspect to the relation, this null equivalence relation, and it was basically that either yeah, okay. So it was either that one numerator was 0 and the other one was not, or vice versa. And that was really not anything special to do with like the rational numbers or whatever. So is basically that this relation, I wanted this relation to hold when so we have three things. So first, either just A and B are the same and M and N are the same. And so I can do that in any such system. I haven't actually specified up here whether I want these sort of more general ones to be monoids or whatever. I haven't really said like what structure I want them to have, and I'm purposely leaving that out because I'm going to figure out what I actually need in order to do what I'm looking at here. Like that's, I'm going to go back now and say, okay, what did I really do here? Which is the thought that I've been having off and on since I did the previous stream, and I figured I would just live stream myself actually finally really writing something down and thinking about like what did I really do all the way back then when I had this idea before. So either A equals B and M equals N, or A equals 0, and okay, well, let me see what I had over here before. Was I said A equals 0 and M is greater than 0, and then B is 1 and N is M minus 1. But there is yeah, so I suppose that here I did actually want to use the fact that it's like going down a stage. Right. So I suppose that I do need subtraction in order to do that. Let's see. I need to think about what I'm actually asking for. So I can say, well, A is 0, and well, in general. So I said M is positive, but maybe it's enough to just say M is not equal to 0. Let's see what else. Well, if that's like having 0 over divided by 0 some other number of times, and then what I said over here was B is equal to 1. Well, I guess that means there has to be a constant. So I guess over here this is what was 0a, this was 0b, big B, that was that other system, and then for my little b, let's see, b is equal to 1. I guess in order for this to make sense, there has to be a 1 in the system that is the A system, that was like the rational numbers, and then N should be equal to M minus 1, and I guess then that would have to be the 1 in, okay, there would have to be a 1 in the system B. Okay, So in order for this to make sense, if I'm going to use the same or a similar definition where I say m is not equal to 0 instead of m is greater than 0, so I don't have to enforce an ordering, then I guess that means that what these things really had to be were actually magmas with 2 constants. At the very least, I need sets with binary operations and 2 constants, and well, one of those constants. So one of those constants is what I'll call 1 for the system A, 1 for the system B. Now, it happened in our previous examples that we usually thought of those as being the same number 1, but I want to just leave it kind of open to see how much I really need about those systems instead of just assuming all of the structure that I had before. Or the third possibility was the symmetric thing. So I have the little a is like 1 in the system big A, little m is n minus 1 in the system B, and then then B is 1 in the system A, and then oh, sorry, no, 0. That was just copying the same thing I had before. 0 in the system A, and then here we have that n should just be not be equal to 0 in the system B. Okay. So that whole like null equivalence relation can be defined anytime that we have 2 systems that have a single binary operation and 2 constants. And probably the interesting thing here is if these actually act as 0 and 1 for their respective systems. So in other words, 0a times just anything is equal to anything times 0a is equal to 0a. In other words, it's an absorbing element or like a 0 for the multiplication, and similarly, 1a does what it's supposed to. It's like an identity. So that should be the same thing as x times 1a. And that should just be x for any x. And similarly for b. Okay. So I haven't used much more than that, and I really don't need those properties like necessarily, but they seem like reasonable things to assume. That's probably what I'm going to want. And so then the real question is, what is the multiplication in general? And so, well, let's see. The multiplication is telling me that if I have AM and BN, like before, the multiplication rule, maybe I'll do circled dot, I guess. Why not? There's only so many symbols. So that multiplication, or why don't I just do a big dot? I haven't even done a dot yet. Why don't I just do a dot? This multiplication is telling me, well, there's going to be a couple cases. So it's going to be, well, let me take a look at how I split this up before. So the cases, the one really different case was when, first of all, if A is not 0 and B is not 0, I can just do that. Okay, and then if A and M are both 0, something else happens, and B and N are both 0, something else happens. Okay, so let's see. So it's exactly the same kind of thing here, but if I write it in my notation here, and then this was this, so that when that was when A and B are not equal to 0. Just double check. Yeah, when A and B are not equal to 0. Okay. So when A is not 0 and B is not 0, then we just do like the obvious thing, and this would be like what's called the product of the two algebraic structures, where you do everything component-wise. Like you just take the first entries and you combine them in that system. You take the second entries and you combine them in that system. So that's like the familiar. That's sort of the familiar product. But we have a slight tweak on that. So when a is equal to 0, then instead, when a is 0 and m is 0. So when a is 0 and m is 0, then instead we get b, and then let's see. Alright, this is bothering me a little bit now, though. Maybe I was actually a little too quick about this. So, let's see. So here I said if a and b are not 0, then this is fine. So if a and m are both 0, then that's like saying this is really like the number 0, and it's times b divided by 0 some number of times. Okay. But if n was 0, then I'd get 0 sub negative 1 here, which I don't want. If n is 0, then I want to do like 0 times b just gives me 0. So actually I needed another condition on this, and this wasn't correct before. This isn't what I wanted. So when a equals m equals 0, and let's see, n is greater than 0, or it's just not equal to 0, in other words. Right, because if n was 0, then I would get 0 sub negative 1 here, which isn't even defined in this set of rules that I had come up with. So that can't be the case. So and n is greater than 0, and similarly here we'll say and m is greater than 0. And the case where they are actually 0 is already taken care of. Let's see. Yeah, I think I was being a little too sloppy here, because I thought that I had covered all cases without having to do too much work. But let's see. So if a and b are both not 0, then I can just do this, and that seems fine. That also covers the case when m and n are both 0. I see what it is. Yeah, there really do need to be more cases, and I was being too optimistic about it before, unfortunately, because if m and n are both 0, that's like saying really a and b are just fractions, and like there's just rational numbers and there's nothing else going on. So you can just multiply them like normal, and then this does what it's supposed to. But that doesn't take care of the case when a and b are, when one of those is 0, when you're multiplying 0 by a rational number. Although I guess, let me think about this. If you were ever multiplying 0 by some rational number, then, let's see. Certainly I need this restriction, because otherwise this wouldn't make sense, but let's see. If I was multiplying 0 by a rational number, I'd have a was 0, m was 0, n was also 0, and then b, if b was anything else, then I wouldn't have any rule that this applied to. I see. So I need separate cases for when a is equal to m is equal to 0 and n is 0, and I need when b is equal to n is equal to 0 and m is 0. I need those separate cases because otherwise this doesn't work. I see. Yep. So unfortunately, this actually does need some other cases to even be correct. I mean, maybe not too shocking because I didn't exactly write out like a proof that this actually covered all the cases previously or that sort of thing. But yeah, this actually was not. This actually was not enough before. So it's going to be 0 when m equals n equals 0. And similarly, when b equals n equals m equals 0. Yeah, unfortunately, those cases do have to be singled out. It seems that that's the case. So yeah, it's basically that either one of these guys, a over 0m or b over 0n, one of these is really the number 0, in which case either the other number is really a rational number and the product is just 0. That's those last two cases I added. Or the other number is really some rational divided by 0 some number of times. That's a positive number of times, in which case multiplying by the rational number 0 knocks it down a level. That's what the n minus 1 or m minus 1 is. Or both of them are some numbers which are genuinely not 0, divided by 0 some number of times, and then you can just do this. Okay. So really, it's like, yeah, there's like those three possibilities. Okay, and so that means over here, I have similar possibilities, which are what? I either can say b and then n minus 1a, when what? When okay, when am is acting like 0, so a equals m equals 0, and n is not equal to 0. I see. So here I really did want the ordering, because I really don't just want to say m is not equal to 0. No. Oh, okay, I see. Yeah, no, I can say n is not equal to 0 here because I was using the natural numbers before. So saying n is not 0 and n is greater than 0 works either way, but I want to say n is not equal to 0 here because I think that will actually make my life better for some reason. I have the feeling that that's like the correct thing to do in general, instead of asking for the ordering. Okay, and so then I have the analogous case here. So when b and m, oh, this is supposed to be n. Oh, and this is supposed to be b. Okay. So here's 1b, 1b. Where did I actually need the 1a here? Oh, I see. Okay, because that's how oh, okay, I see. So m, yeah, a m minus 1b when b is equal to n is equal to 0, and m is not 0. Okay. And then finally I have the cases where I just get that the result is like 0, 0a, 0b, so either when a equals m equals 0 equals n, or b equals n equals 0 m. Okay. So yeah, so all of these rules are definable in any system that just has any pair of systems where there's each one has a binary operation, each one has a 0 and a 1. You don't really have to ask that they have these properties, but it's probably natural with whatever we're doing here to just say, okay, let's just assume that they have 0 is a designated thing that acts like 0, 1 is a designated thing that acts like 1. And I'm going to think about, like, you know, what it is that I'm really doing here, because this construction doesn't actually have any more to do with the natural numbers or the rational numbers than that. I can take any pair of algebraic structures that look like this, and I can do this thing to them to make a new one that has the division by 0 kind of thing going on. And so, so that's something that I can do with any two such systems, and I kind of like to think about what it is that I'm doing here. Are there any questions so far? Comments? Yeah, this is the general thing I wanted to start thinking about. Was what I really described doesn't have anything to do with the rational numbers or the natural numbers in particular, except maybe in the extent that they have a 0 and a 1 element that are identified. So the way I'm kind of thinking about this is that it's like, this is like, I mean, this, you know, even though it's not really necessarily, you don't have to think of it to do with division by 0, this is like that number of times you've divided by 0, or sort of like the level of infinity that you're on at the moment. And the reason I think that's interesting is because now we can say, well, what if I do this when instead I take A to be like, let's say that I take A to actually be or let's just take both A and B to be the rationals, with like the usual multiplication, the usual 0, and the usual number 1. Oh, I guess I didn't indicate the universe in these like I usually do. If I was being a little more careful, I'd put like A without the underline and so forth, but that's fine. So what if A and B are just the rational numbers? Oh yeah, so my intuition is basically that I'm thinking of AM as representing like A divided by 0 like m number of times, which I was writing like that before. And the idea is that, well, if I had the number that was actually 0, which is like, I guess, 0 divided by 0 number of times, if you want to think of it that way, then I know that 0 times, something else over 0 some number of times, if it's divided by 0 some positive number of times, I want that to take it down by a number of times. Or in other words, basically the generalization of saying 0 times 1 over 0 should give me 1. So yeah, I'm basically just saying, okay, this is the one new thing that I want to do, and I need to adjust everything to make sure that I like do that case, that I cover that case. And then yeah, I'm just working backwards to find the simplest way to express that in terms of what I already have without contradicting myself somewhere. And so that's why I realized actually I had missed this last case before, because I was just checking them and I realized, oh, I missed one. So yeah, I just need to cover all the possible multiplications without contradicting myself, and yeah, that's basically what it is. I know what I want. I mean, that's sort of what the whole like constructing a free algebraic structure, or the even the more fancy version like of the free algebra given some presentation. It's basically just I'm going to do the laziest or most like sort of obvious thing that I can to start off with what I want. It's like saying like kind of the shape of what I want, and then just following that to construct all of the elements of that algebraic structure. Yeah, maybe I can give more examples of that in a minute to make that make more sense. But it's like, although it sounds fancy, it's actually the laziest possible thing that you can do, in some sense. But yeah, that's kind of my intuition behind it. I need to find the rules that make this make sense with the system that I'm talking about. Did that make some kind of sense at least? Well, oh yeah, oh perfect, yes, do it in a lazy way that sounds impressive. Yeah, so, I mean, it really depends on exactly what your inclination is, but, if your charisma and sales ability are high enough, you can 100% just get by on that, because you can, you just have to convince people that you're very fancy and impressive, and you don't have to actually know about anything in particular. It's certainly possible. Yeah, I mean, depending on your particular area, it may be more or less difficult to actually do that in practice, because sometimes people will actually try to analyze what it is that you're doing, and if you're completely full of it, then people might know. But yeah. It's definitely possible to get by depending on the area, but yeah, yeah, it's a balance. You've got to sell yourself, but like most of us don't have the charisma to get by 100% on just just complete bluster, and so we have to actually be good at what we're doing too. Yeah, so. Yeah, so I'm basically trying to come up with rules that make this work the way that I want it to work, and fortunately I have been able to come up with some rules that at least do this kind of multiplication part of it. And so what I wanted to think about really was, what if I do this construction where everything in sight is a rational number, where all of these things are rational numbers, and I'm just doing the do I want to do multiplication, though, I guess is the thing. Well, why not? Let's say I'm doing multiplication for both of them. So before this was like addition of counting numbers. I'm just going to make them both multiplication and see what happens. So so what does that mean? That means that if I have am, and I define this weird dot operation, combining it with bn, then what I'm saying is that, well, by definition, this is going to be the product of a and b, which are fractions, like actual rational numbers, and then the product of m with n, when what? When a is not 0 and b is not 0. Okay, so that's just the usual multiplication in what we might call, this is like what we might call q squared, pairs of rational numbers. But then we have the other cases to consider. And so, let's see. In the case where a and m are 0 and n is not 0, so I said n minus 1 before, and actually I didn't think very carefully about what I was actually asking for here. So over here, it was fine to say, well, I could think about it as like the 0 should be absorbing anything times this 0a should be 0, and 1 should be like an identity. And that seemed consistent with what I was like intuitively trying to come up with. And then I said, oh, it's like the same kind of thing here. But I was actually being pretty lazy, and really it's not the same thing, because here I'm asking that 0 is not absorbing. The role that 0 plays here in the example that I had was that 0, and then remember, if these are like the naturals, 0 plus anything is actually, well, that thing plus 0, which is that thing. So this 0b should be the identity, the additive identity. It should be the identity for this operation, not an absorbing element. And then this 1, well, it's a generator. Additively, it's a generator. You can make any number by adding 1 to itself a certain number of times. You can make 0 by adding 1 to itself 0 many times. It's like the empty sum. But I'm not really sure that I'm not really sure how relevant that is, except that it's a particular element that we chose. And so again, I didn't really need any of these properties to define everything that I've defined so far, or make it consistent or anything like that. So now that I think about it, actually saying that I want to subtract 1, well, actually, first of all, I didn't really define what subtract means, because I actually need to think about that a little bit, and it shows up here as well, because okay, so I guess what I mean is actually that 1 is something that I can so I guess 1 is something I can subtract. So I guess what that means is x plus 1b equals y has a solution. Maybe I should even say, in order to make this well defined, I need to say it has a unique solution. For each choice of y. In other words, I can actually make y minus whatever this thing is make sense. So I need a system that at least has that. That's actually something that I really need. The rest of this is more optional, just to define what I have so far. But I really need this to be true, or else I can't make any sense. Oh, and I guess I should do the circled plus. I really can't make any sense of what I mean by subtraction here. So what I mean by subtraction here, or maybe I'll do circled subtraction. What I really mean is the unique solution to that equation. Otherwise, there's no real way to make sense of what I mean by minus for just some system. Okay, and so so that's actually what's going on here. I need this to be the subtraction in that sense, the unique solution to the appropriate equation. The thing that when you add 1b to it, you get m, where add means do this circled plus thing. Okay, so now equipped with that, I can actually think about what this is supposed to mean. If these are rational numbers, and here I'm supposed to end up with b and n minus 1b, well, okay, maybe before doing that, let's think about what it's supposed to mean. If I'm using the rational numbers for these, to have a solution to to x times y, no, not y, what do I want? To x times 1 equals y. Well, the unique solution to that is just y. There's only one solution to this equation. It's just y. Y times 1 is equal to y. If these are actually fractions, actual rational numbers. So that means that here I want b and then n minus 1b, but that minus 1b, so b And then really that's basically saying n divided by 1, which is just n when a equals m equals 0 and so a equals m equals 0 and n is not equal to 0. Okay. Huh. Yeah, so, well, I mean, I wanted to see what I got, and I got something that was, a little surprising to me, in that what this is saying is, what this is saying is that if n is not 0, and you multiply by like something that looks like 0, 0, 0, with this weird dot operation, you're just going to get back the same thing that you started with. So it's kind of like saying that this is just absorbing. This is just like absorbing 0 instead of getting like knocked down a level. It's like it's absorbing. It's like it's absorbing 0 instead. Which, like, you know, okay, that's it's something. I mean, I guess it's because in my original example, I had that 1 was a generator for the algebraic structure, so it made something more interesting happen. Whereas here, 1 is an identity element, and so dividing by it or undoing it is not really doing anything very, very interesting. Well, that's what that is, and for similar reasons, this will just give me am when b is equal to n is equal to 0, and m is not equal to 0. And then finally, well, according to my rules up here, I get 0, 0 when you know three of them are 0. So I get 0, 0, which is sort of like the new element that's like the element 0 in some sense, when a equals m equals n equals 0, or b equals n equals m equals 0. Okay. Well, so that's something. That's you know, I don't really know what I expected exactly, but like that's certainly some system which has the same exact relationship with the two structures that I started with as the original example I gave with division by 0. This one has a lot more like absorbing elements, because before, like doing something that was like you know 0, 0 combined with like, you know, well, I'll do a specific example, like, you know, 3, like 4 or something. Before, you would get something that was like, okay, this is like knocking this down a level, and you'd get like 3, 3 instead in the original example that I gave you before. But now in this new example, because things work differently, this actually just isn't having any effect at all, and we're just getting 3, 4 back again. So yeah, so all of these elements absorb 0, 0. Actually, instead of acting like 0, it's acting like an identity element with respect to this operation. So, I mean, that's not necessarily good or bad. That's just what this odd construction looks like. So that's one example anyway, and so so I guess maybe I'll give one more example. Do people have any questions or comments about this one? This is just another sort of similar thing like this, and I guess just to give some more intuition, maybe I'll also say this is it's kind of like saying if I want to do a divided by 0 m times, and then b divided by 0 n times, it's like saying you can be dividing by 0 a fractional number of times, and then the rule is basically like you do this, a, b, or 0 m times n. Pretend that says the letter m and the letter n. You know, and then there's those exceptions if actually one of your a over 0 m or b over 0 n is you know, really the number 0, is basically what it is. So I mean, that's well, that's something. Yeah, so I do have that example. There's also another example that I was curious about, which maybe I'll tell you about as well, where I make maybe a more obvious change that I just didn't do before now. So there's another example where what happens if I take my first thing, my like numerators, to be well, say still the rational numbers, equipped with the usual multiplication, the usual number 0, the usual number 1, but I take the thing that I was calling b to be, well, yeah, let's say the integers, so positive and negative counting numbers and 0, with addition, and then the number 0 and the number 1. Well, if I do the same thing here, where this is now the integers with addition, then I'm allowed to form things like 3 divided by 0, like -6 times. And if I multiply that by something that's like 2 over 0, like positive 3 times, then the idea is that, well, we should multiply the numerators, and then for these indices we should add them together because I have addition here now instead of multiplication, and we should get something like 0 sub -3 instead. And so the reason why I think this example is interesting is because this one actually maybe looks a little bit more like what we would expect with a system where we had like infinities and infinitesimals, because we could think of dividing by 0 -6 times, kind of like this is kind of like playing the role of saying take your number and multiply it by 3, and then multiply it by 0, and then multiply it by 0, and so on and so forth for like 6 times. And you might say, well, you know, what's the point of thinking of it like that? Because you know, doesn't just multiplying by 0 over and over just make it 0? But remember, this is supposed to be like the division by 0 kind of system of arithmetic, and so we saw examples before, right? Like where I took like 1 over 0 and multiplied it by 0, and then multiplied it by 0 again, you know, and well, okay, then I get 1 times 0, which is 0, but you know, on the other hand, if I did it the other way, I get something else. Get 1 over 0 times 0, which is 1. So remember, it matters what order the parentheses go in. You can't just collect all the zeros together just because, you know, you could in the traditional system, but this one definitely doesn't have that associative property, so it just, you know, it matters. And then the reason why these are interesting is because we had said, well, you know, we'd really like to be able to solve all like division problems that we were interested in solving, right? But if we wanted to solve a problem like, you know, what, you know, if I have like 2 over 0 and I want to multiply it by something, and I want to get and I want to get like, say like 5, right? So in other words, I want to be able to form something that's like 5 divided by 2 divided by 0, something like that. Well, if I multiply it by 0, then I'll get 2. But then it's kind of like I'd need to multiply by 0 and then multiply by something again in order to in order to get 5. And so if you notice, I can't just multiply by something with, I can't multiply by another counting number, another rational number, and if I multiply by something with zeros in the denominator, like 4 over 0, well, I'm just going to get something over 0 like twice, and that's definitely not 5. So I'm kind of missing solutions to equations like this, but this looks like it's putting back in something like that. So okay, so that's kind of my hope anyway, that this will do that this will do good things for us. So here, maybe let me can I actually like select and like copy? Can I just copy this? I just want a copy of this. Can I like, what happens if I copy and then paste this? Ah, yes. Now I can have more of these. I'm getting better at lecturing on this thing. But you know, it doesn't just have to be a one-way lecture. Like, please let me know if you have any questions or comments. I think this example is going to be more interesting because I think that I'm going to be able to solve more division problems in it. And you know, if you want a system where you can divide by 0, you'd think, well, I should be able to divide by anything. That's kind of the goal, right? Is that all division problems should be solvable. But the original example I gave definitely doesn't have that. So let's see if this one does a little bit better. So, well, if I have my AM and BN, this dot is the dot of my weird dot operation for my division by 0 type systems. This dot up here is representing just multiplying fractions like normal. Okay, so, well, of course there's the possibility we have AM, and then we're back to this, AB rather, and then we're back to this being M plus N when A and B are not 0. Okay, and then, well, if A and M are both 0, then we get B, and then here we have N minus 1. So when A, M are 0, and N is not allowed to be 0, and then similarly we get A, M minus 1, when B is equal to N is equal to 0, and M is not 0. So it like knocks them down a level. And so then, well, then we have just 0, 0 when those two other cases. When A, M, and N are all 0, or when B, N, and M are all 0. Okay. So that looks quite similar, but there's an important difference, which I will now illustrate by trying to solve one of these division problems. So if we use those rules and we say, well, if I have AM times BN is equal to some CK, well, let's think about what happens in various cases. So these are sort of the special cases that are like not the typical situation. Those are sort of more rare things. So in the typical situation, you know, so here maybe I'll do this. This is case 1, this is case 2, this is case 3, this is case 4. So, well, in case 1, what is that? What happened? If we did this operation and we got this, that means that AB M plus N is equal to CK. So AB is equal to C, M plus N is equal to K, and well, we also know some other stuff because we're in this case. We know that A is not equal to 0, and B is not equal to 0. So we know all of that. Okay, so, well, what can we conclude from that we can conclude, for instance, that that A is equal to C divided by B. Those are just rational numbers, so that makes sense. That's a totally reasonable thing. And we can also conclude that m is k minus n, and these are integers now, so I can always do the subtraction. Even if the result ends up being a negative number, I don't care anymore. That's fine. And so that means that actually I can solve this division problem here, and if I wanted to write it this way, I could think of it as being, as telling me that ck divided by bn should be equal to, in this case at least, should be equal to c over b and then k minus n. So that's case one. And we could do the same thing for saying, instead, like thinking about it like dividing by am instead. So we could solve that division problem. So that's encouraging. Maybe I'll actually write the other one here too. If we did ck, perhaps just suggestively I'll write divided on the left by am. Just kind of thinking of it, this as being like dividing by this on the left, dividing by this on the right. So here we'd have, well, still c divided by a, and then k minus m instead, for similar reasons. Okay, so we can solve division problems if it happens that we're using case one of the multiplication rule. And so, well, then what about case two? So in case two, so a and m are 0 and n is not 0, so maybe I'll just write that down first. And what else happens? A and m are 0, n is not 0, and so it looks like we have that the product, which is like ck, is b n minus 1. So b n minus 1 equals ck. All right. Well, what does that mean then? It means that we could. Well, how do I want to say this? Okay. So this b n minus 1 is the product of. So here we have 0, 0 times. Well, bn, where we just know that n is not 0. And so in this case, we can see that b equals c. So b and c have to be the same thing. And we can also see that k has to be n minus 1. So, well, what's that telling us then? That's telling us that if we knew this thing and we knew ck, then we could figure out what bn is, because we would know that b had to be c and n has to actually be k plus 1. So in other words, this is telling us that if I do ck divided by like 0, 0 on the left, then the only possible solution to that is going to be if if we have that b is c and n is k plus 1. Okay, so we can like divide by 0, 0 on the left. Let's see what happens if we want to divide by bn on the right. Well, the only way that this equation could be true is really if b was c and n was k plus 1. So all that we'd really be saying in that case would be that if I take ck and I divide by ck plus 1 on the right, then what I should get is 0, 0. Okay. So we do need to be a little bit careful, because if we look at the different cases, we might conclude that there's more than one reasonable value for one of these, and that would just mean that the division operation wasn't actually well defined. But what I'm going to do is I'm going to list out all the possibilities, and then I'm going to sit there and I'm going to say, okay, now is it possible that two of these will apply to the same situation and then will contradict each other, or does this actually make sense? So right now I'm just writing down all the possibilities. Okay, so yes. So this is the case when A is not 0 and B is not 0. Oh, but all these cases, okay, so, right. Well, okay, I'll have to think about it. All right, so, okay, because I guess this, right, so like for instance, in this case, A is not 0 and B is not 0. Well, that means C cannot be 0. So this is like saying, if I want to do this right division, if I know that C is not 0 and B is not 0, then I can do this. Similarly here, if I know that C is not 0 and A is not 0, then I can do this. So then the only cases left to consider are like when one of those is 0. So here, so here, for instance, I'm saying, okay, these two, I know these two are 0, and I know that n is not 0, which I guess means that k is not -1. Okay, so yeah, there's like a list of conditions. There's like a list of conditions for each of these, for each of the division rules. Okay, and so then case 3 will be similar, and well, what'll case 3 say? It'll say that am times 0, 0. Okay, so this is the b equals n equals 0, but m does not equal 0 case. So it'll say that, well, the same kind of thing. Oh, are you okay? Okay. So let's see. It'll say that, well, this is CK. And so for very similar reasons, this then means, okay, that means that A would have to be equal to C. M minus 1 would have to be equal to K. So K plus 1 is equal to M. And so, well, again, for very similar reasons, this says that CK divided by 0, 0 on the right now would have to be, well, AM, which would be C, K plus 1. And it says that if I had, it says that if I take CK and divide it on the left by AM, then I should have to get 0, 0 in this instance. Oh, but in what instance? When A is C and M is K plus 1, which is like the same, basically the symmetric thing to what I had in the previous case. Right, CK over C, K plus 1 is 0, 0. Okay. All right. Hey, buddy, are you okay? Debbie, come here. Debbie. Okay, he's too curious about something out the window right now. We're still gonna get Dobby emotes at some point. We're gonna have some kind of dog emote with a little picture of Dobby on it, and yeah, it'll be great. It's gonna be really nice. Okay, so now I'm most of the way through the cases. The last one is what happens when all three of the things are 0. But maybe even before that, I'll think about, like, just, are these cases consistent with each other? So these are telling me, like, how I can solve these division problems. And it's basically looking like, whether it's on the left or the right-hand side, it's basically looking like if C and the first entry and the other thing are not 0, Debbie, it's okay, buddy. Debbie, Who's a good boy? Do you want your toy, buddy? You want this? Are you ready? Get set. Go! Ah, he got it. There's not much room to throw it right here, but he got it. Yeah. Yeah, get it. He got it. It's like a little wheel. Okay, so this is basically saying if the first entry in the thing you're dividing by is not 0, and this thing is not 0, then you can just divide them. Oh yeah, that's a great idea. You know what? There are animated. I remember now. Twitch has the capacity for animated emoticons. I've seen it before. I haven't looked into, Nova's more the art person, so I haven't looked into how to actually do it, but it is possible. Yeah, it is possible to make animated emoticons for sure. Oh yeah, that's right. I was just talking about Darwin fish the other day actually, but yeah, there's the original Jesus fish, then there's Darwin fish, and then there's Gulpo, the fish that eats concepts. There's like layers to it, but this is gonna be Dobby, the dog that eats math. Buddy, are you okay? I think there's just people living their lives out there, bud. It's all right. It's okay. They're just doing their thing. You're a good boy. It's good guarding. All right. He just needs reassurance sometimes. Okay, so let's see here. So this division makes sense whenever the first entries are both not 0. And it's sort of like the obvious choice for how division's supposed to work. So then what about these? These are basically saying when you divide by something that's like 0, 0, and when you divide by something that's like 0, 0, and what do we know here? Oh, there's just other dogs out there, bud. It's okay. There's just other dogs out there. Dobby, it's okay, buddy. It's okay. I know. Just shake it off. All right. I think he's just gonna have to go. Hey, Dobby. Go over there. Oh, I threw his toy, but it didn't go. All right. Yeah, so let's see. So if you divide by something that's like 0, 0, then you just kind of bump the last thing up a notch. It's like dividing by 0. Oh yeah, that's fair. It was a real tragedy for number theory when people figured out that cryptography was a thing. Yeah, I mean, it's just because we all endeavor to just spend our lives just toiling away at just completely meaningless nonsense, but sometimes despite the best of our intentions, something ends up becoming extremely significant, profitable, dangerous, whatever the case may be, and then you just have to live with that. Yeah. We can't all be so lucky as to toil away in obscurity. So let's see. If you divide by 0, 0, you're basically bumping the second coordinate up a notch, is what's happening. And if you divide by the same thing that has the second coordinate already bumped up a notch, then you get 0, 0. So there are some conditions on this. Well, the b equals n equals 0 is just putting in the 0, 0, so that's not really a condition per se. But this is saying m is not equal to 0 here. But what does that mean for these? For these things, it means that when k is not equal to -1. And similarly for these are true as long as k is not equal to -1 for the same reason. And then for these two cases here, Well, these are true. These are true when C is not equal to 0, and then A is not equal to 0, or B is not equal to 0, as the case may be. So these are the ones where the first two coordinates are not 0. These ones hold as long as K is not -1. Okay, but well, here's something right here. So in particular, this first case would hold when both of these first entries are the same thing, like C that is not 0. So in other words, that's telling me that if I do CK divided by CK, well, C is not 0, so this should be C over C, K minus K, and that should be 1, 0 by case 1. But then also, oh no, I need K plus 1, not K plus 1 in the second coordinate, or else this isn't going to be interesting. Okay, so now this should be C over C, and then K minus K plus 1. And so I should get 1 and then -1 here. Okay, so, right, so that should be that by case 1, but on the other hand, CK over CK plus 1, just assume C is not 0 here, CK over CK plus 1 should be equal to 0, 0 by case 2 or 3 or whatever it is, the other one, 2, I guess. So we have solutions to equations, but we don't have unique solutions to equations or to division problems, because these two things, according to our rules, these two things aren't equal to each other. So they're not equal to each other, but they're both a solution to that division problem. So really, this equal sign should be, sort of in scare quotes, like the idea is that these are both solutions to that division problem, but it's really not proper to say that this division is well defined and is equal to each of these things, because they're not supposed to be equal to each other according to our, they're not related according to our equivalence relation. Yeah. There is a solution to each of these division problems, but there's not necessarily a unique solution. Okay, so maybe I'll just put here solutions to division problems are not unique, but they exist. There is a solution, but at least we have at least one solution for all of those cases, and then there's still a case, case 4 to consider, which maybe I'll do just briefly since it's that one's pretty straightforward. So for case 4, well, what happens? That's the case where you have, like everything except for B is 0, so 0, 0, is B 0, is 0, 0, which is CK. So that's like the A equals M equals N equals 0 case, and so, well, in that case, what are we saying? So C is 0, K is 0. So it's saying, if I divide on the left, if I have, this must mean that C is 0 and K is 0. So if I divide on the left by 0, 0, and now you can really see, I'll just put scare quotes around the whole thing. You can see why this doesn't look like it's reasonable, because it's saying that there's anything that's like B0 as a solution to this. Certainly they can't all be the same solution. So this has infinitely many, solutions or things that make the equation true. But if you think about what this is saying, actually, what this represents, dividing by 0, 0 many times, it's like, really, this is just like saying, well, what are the solutions to 0 times b equals 0? Well, you could choose anything you want for b if b has to be a rational number, it's a fraction. So, like, it's really just like saying this, or that, that has infinitely many solutions. Just like, okay, that's not surprising. So, all right, so even if we looked at just this case, we'd already see that that was what was going on, and that persists into these sort of other levels as well. So we do seem to have solutions to all of these equations. There's always at least one solution to any kind of division problem that we want to write down. And then similarly, similarly, we can also say, if I want to think of this as like 0, 0 divided on the right by b0, then I should get 0, 0. But again, it's maybe best to think about this as being, in scare quotes. What am I trying to say here? There's a unique way of assigning that, actually. Because it's just like saying 0. This one doesn't need scare quotes, because this is just like saying 0 divided by anything is 0, which is like, okay, that's fine. So unlike the original example that I gave, what's interesting about this is actually that it's possible to solve any division problem that we can come up with in this system, because these cases covered all, assuming that there's, I didn't miss anything, these cases cover all the possible situations. Oh, where am I? So it's here. Yeah, these cases cover all the possible situations when I'm multiplying two things in this system. So that means that every division problem is solvable, and it's just that there's usually more than one solution. So you can't really form fractions in the same kind of way, but like every division problem has at least one solution. So like there exists a solution to the division problem, and so that's kind of nice, in the sense that means that this is a property that was missing from like the traditional multiplication of rational numbers, right? There were division problems that we couldn't solve, for instance, there was let's see. So for instance, in the usual, system of rational numbers, things like 0 times x equals 5, have no solution for x. But now we've made a system where any similar kind of equation like that always has at least one solution. We can't guarantee that there is a unique solution, but there's at least one solution. And so, that's actually pretty nice. This is a kind of answer to how can I make a system that contains the usual multiplication for rational numbers, at least, where I can solve any of these equations, but it doesn't really. It's maybe not super satisfying in the sense that. Maybe you accept that we shouldn't have unique solutions to equations, because even in the rationals, there are many solutions to the equation, like, 0 times x equals 0. This has you know, infinitely many solutions. So like maybe it's not surprising that there's some of them that don't have a unique solution. But you might say, well, you know, it's kind of frustrating that we can't add these things though, right? Like we'd want a system where you can have at least one solution to each division problem and then add things as well. But none of what I've said so far has to do with addition. You know, it's just about multiplication. And so, you know, I mean, it's conceivable that you could try to sort of, come up with similar rules for addition. Like presumably, you'd want to be able to have like a, some kind of common denominator. Like how do we extend this to addition? You know, if I want to add something like 1 over 0 plus 5 over 0, it seems perfectly believable that that should be 6 over 0. But what about 1 over 0 and 3 over 0 sub 2? What's that supposed to be? And I mean, you know, in the setup that we have so far, we don't really have a way of making a common denominator, in the sense that I can't just like say, oh, I'll put a 0 sub 2 here and then put an extra 0 in the numerator, because that's not the system that we have. You know, like that notion isn't really compatible with the system that we already have in place. So it seems like that might not really work to like get a common denominator. Yeah, unfortunately, it seems like that's not really the most helpful idea. So I think that if our desire was to get a system that had this sort of property where division problems were solvable in some sense, maybe not uniquely, but were solvable, and where we could also add things together, it seems like it's going to be hard. It's going to be hard to do it using this construction. I'm not saying that it's not possible to somehow extend this, but it seems like it's going to be hard. And so instead of trying to kind of like ad hoc, like build up examples like this to try to get closer to what we want, the notion of like a free algebraic structure with respect to like some constraints is I know that's kind of maybe sounds ironic, but like the notion of a presentation basically is very helpful in this regard. So I'm maybe not going to give you a formal definition, but I'm going to kind of motivate like a different way that we could think about this that's different from just saying like I'm gonna just try to keep pulling out examples until I find an example that it does the thing that I want, which in principle could take forever, right? Even if your intuition is okay, like maybe it'll just take forever messing around with different examples. It's possible. So instead, like, a good thing to say is like, what do I want here? Well, it seems like the thing that was really desirable and the thing that motivated me when I was younger to messing around with this was really that I want solutions to those, division problems in a way, right? I know that I can't have unique solutions, perhaps. There's like nice examples. I can't have unique solutions to division problems, but I can still have solutions. So maybe I want to ask for something that has addition and multiplication in some sense, but it doesn't necessarily have, it has solutions to division problems, but maybe not unique ones. So what does that mean? So what do I want? So I want some kind of algebraic structure in the sense of universal algebra. I want an algebra, say A for algebra, with some kind of addition, some kind of multiplication. Well, maybe I'll even say 0 and 1. That seems plausible that I would want those. Where what? Where well, so the thing is, I can certainly have algebras with that signature. I can have a set with a pair of binary operations and a pair of constants that are specified that satisfy no constraints. So that's the easiest thing to accomplish. I can definitely have that. Like that I can come up with an endless amount of examples for. Very easy. So the next question is, well, okay, what do I really want? Where each well, where maybe I'll start making a list. 1 for all x and x and z in our universe, there is some y with x times y equal to z. And then similarly, I'll ask it on the other side. It might not actually have to be the same y, or maybe I'll say sort of the symmetric thing. So for all, well, I'll say it this way. For all y and z, there is some x in A with x times y equal to z. It's not the same thing. It's just like saying you can divide on the left and divide on the right in the weak sense of like that there is a solution. It's not necessarily that there's a unique solution again, but just that there is a solution. Notice this already is a property that like the usual number systems don't have, because I'm not saying you can solve this when x is not 0 or whatever. I'm saying for all values, including 0. So definitely I want this. This is already something which the usual systems do not have. Okay, so that's possible. And then I can say, well, what else would I naturally want from such a system that's reasonable to ask for? Well, if this is really going to be interesting to me at all, then 0 times x should be x times 0 should be 0 for any x. That 0 thing should be like an absorbing element. And then, probably at least some of the other axioms that we would have for a ring, so probably we would want that this is a multiplicative identity. That seems harmless enough. I mean, it all seems harmless enough until you find a contradiction, but for any x. And then also 0 should be, an additive identity. 0 plus x should be x plus 0. Should be x for any x. Okay, so I should be able to ask for that. Now, if we think about this for a minute, what I've already done here is enough to show that this kind of structure cannot be associative if it's not trivial. So even if I just have these axioms, and then maybe I'll add more, who knows, but just with these axioms already, I definitely know that this can't be associative. So I can't ask, for instance, that this thing actually be a ring, right? Because, well, if if 0 times alpha equals 1, right? this exists. This exists by some axiom that I just wrote down. Axiom, whatever. 1, I guess. By the first axiom. So there has to be such a thing. This is like the 1 over 0 thing. So if there is such a thing, then, well, then 0 times alpha is 1, but 0 times alpha equals 0 by axiom 3. So, well, that means that 0 equals 1, so this is trivial. I said I can't have associativity, but I realize now this is just a true contradiction. So I was thinking I was going to just cook up for you like the general form of the this is not associative example to say this can't be a ring, but what I actually just showed you is that this is just blatantly a contradiction. So I can't say for any x that 0 is an absorbing element. Yeah, so, So I certainly can't have that. And I mean, I didn't have that in the examples that I had, actually. This was too strong. And since I don't really have a way, just when I am given a whole algebra that does the thing that I want, I don't really have a way of saying, no, I mean like the ones that are more like the rational numbers that we started with. That doesn't really make sense in this general context. So I think saying this is probably not desirable. Yeah, so I think I probably don't want that. Seems like it's not gonna give us a good time. So that's too much. I can't ask for that. Oh, but I can think of a different way that I might phrase this that is an interesting question. So okay, so asking for these additional things is probably gonna not be super positive for us. So what if I did something slightly different instead? Well, I know I can have something like this because I can just make one of the examples I had before and then just choose any addition that I want and have that be meaningless, but that's not really what I'm asking for, right? Like that's sort of not really what I want. So maybe I want something more than just an algebra where this happens. Maybe I'll say that an algebra, maybe I'll say that what I really want is an algebra where this happens is, maybe I'll say that this is called, I don't know, I'll say it's called divisible for now. Don't sue me if this is already a word for something else, but whatever, lots of things are divisible. This is what I'm going to use it for. So let's say that an algebra that looks like that is it's called divisible. Maybe even let's extend the signature a little bit further just to be super careful, and let's say I have a notion of subtraction as well. Addition, subtraction, multiplication. I've got 0, I've got 1. Okay, an algebra like that where you can solve all of these division problems is called divisible. What I really want to ask is, given a ring R, first of all, is there a divisible algebra A with R embedded into it? So is that possible? In other words, is it, you know, I mean, is it possible to make something that has solutions to all division problems and contains the contains the ring. You know, that's basically the question. Well, that's you know, that's perhaps a reasonable thing to ask. I haven't actually answered it yet because I've just, so far all I've done is say, well, I can do the multiplication part of it where I get solutions to all the multiplication problems, but I don't have solutions to the addition, to like how is addition supposed to work? That's, you know, it's a good question. So that's, you know, that's a thing. Well, you know, one thing that I could try to do is I could try to introduce, or rather, how do I want to say this? So I can't really make a most general, well, how do I want to say this? The reason why it's hard for me, so it's a little bit harder for me to say, like, what is the most general divisible algebra with a given, that's built from a given set of elements, because I'm just saying that there exists a solution to this equation, but I'm not saying there's a unique one. So, you know, perhaps the most general answer would have, you know, 2 or 7 or an infinite number of possible solutions to each of these equations, and so it's kind of something which isn't. It's not algebra. It's not like it's not an equational thing. I can't define that by an equation. So instead, what I could ask for is just that there's I could make the most general kind of structure that I wanted that had solutions, that had a single solution to each of these equations. You know, but if I did that, well, okay, if there was a single solution to each of these equations, let's just imagine that it's possible to solve the problem this way. Like, let's just to make our lives easier, let's say, you know, suppose that A, which is this thing, suppose that this is divisible, and well, let's say that z divided by x on the left is the unique solution to xy equals z, and similarly z over y is the unique solution to xy equals z for x, and this is for y. Okay, so we could do that. We could say, like, there's like these left and right divisions, and you can divide and you get a unique solution. Let's just suppose that that's the case. Well, if that's the case, then, well, so I guess what I'm asking here is it possible that there's an example of this where the solutions to that division problem are unique? Just in general, like, are there examples of this? Well, I guess if I take any system that just has multiplications where the solutions to the division problems are unique, which I can certainly come up with. Just take like the non-zero rational numbers, for instance. Then I could just assign the addition and multiplication, or the addition and subtraction, to be whatever. I mean, yeah, there's kind of cheap answers to this, but I think that if So I think the thing that causes us problems when we're trying to embed embed a ring into something like this, though, is that we're going to say 0. We want a unique solution to this, but there are manifestly more than there's manifestly more than one solution to this. Like this, this has infinitely many solutions. So there certainly can't be a unique solution to each of these, like if a ring embeds into it. Like that's not going to happen, because in a ring, 0 times anything will be 0, so there are other elements besides 0 that solve this, and so this has an infinite number of solutions. So so you can't have this property if you're going to have a ring embed into the thing. That you're going to have an endless amount of, that you're at least going to have countably many solutions. So let's see. If I want to, so I know that I'm going to want to have a countable number of solutions, at least, in principle, for each of these things. So one way that I could try to deal with this is I could do something that seems a little bit like cheating. And well, actually, can anyone guess how I'm going to cheat and see if I can actually force this to be something that's more algebraic somehow? Okay, maybe not. 0 times. Well, so yeah, I mean that's basically the problem, is that this has infinitely many solutions, and this I tried one way of like making this into an algebraic thing, which is by saying that there's a well-defined division operation where there's a unique solution to each of these, but that doesn't work in this case because I want to stick a ring into one of these, and rings have infinitely many solutions to some of these problems. So I can't force that. That'll ruin it. So instead, what I'm thinking is, well, what if I make a different division operation for each of the possibilities? So the basic issue here is 0 over 0 equals what? Because, well, 0 times 3 equals 0, but 0 times 7 also equals 0, and 3 is not equal to 7. So like that's a big problem for us. So here's what I'm going to do instead to cheat a little bit. What I'm going to do instead is I'm going to say, well, sure, 3 is not equal to 7, so they're both competing for this value of 0 divided by 0. But what I'm going to do instead is I'm going to say that there is an operation. How do I want to say this? So I'm going to say that 0. I'm going to say that 0. Maybe I'll say it this way. Maybe I'll do, I don't know if I can actually get this intact, but maybe I'll do the division sign with like a little 3 over it or something like that. 0 divided by 0, the 3 one is 3, and then the 7 one is 7. And you might say, well, what's the point of doing that? Yeah, so there's different versions of 0 divided by 0, but you might say, what's the purpose of doing that? But then the idea is that I can imagine that there is an operation which is like x divided by, and then, I don't know, maybe I'll say k. No, my k's are too difficult to look at already. I'll say s, y, right? And the idea is that, and the idea is what? Is that if you do y times this thing, you do y times this thing, then you should, well, this is like saying x divided by y. So normally, if, let's see, how do I want to say this? So normally what you would do, you have x divided by y, you multiply by y, you should get x, except in the case where x and y are both 0. So you should get x, except in the case where x and y are both 0, in which case you get s. So s when x equals y equals 0, and x otherwise. So it's basically division, except in the case when both of these things are 0, then you should get x. Okay, but now what I'm thinking is, okay, so this is like a cheating way of making it into a well-defined operation. I'll make a different operation for each result. But that would only make sense if, well, okay. So I want to fix the case when I have it that, you know, something times x equals itself has infinitely many solutions. And so, let's see, in the systems I was looking at before, we did have other absorbing elements as well. When did that happen? Well, in the case, okay, like in this case, no, we didn't actually. Okay, no, so that's fine. Right. So the only things that actually absorbed other elements here were like 0, 0 was 0. Okay, I think that this is okay. Actually, I'm feeling pretty good about this so far. Is 0? Oh. Well, there's not, I mean, I guess it depends on if you have a specific meaning in mind for more natural, because, yeah, because basically what I'm doing here is I'm saying, okay, there's not really a unique solution to the division problem, but I'm going to make a different division operation for each possible result in the one case where it's not well defined, and I'm gonna demand that, you know, the result is just that. So yeah, it's completely artificial. It's literally just a cheat to force something that wasn't algebraic because it wasn't like a well-defined thing into something that is. But the reason why this is desirable is because I can actually make this into like the signature, the rules for a type of algebraic structure, and if I can do that in the sense of universal algebra, then I know that there's a free algebraic structure of that signature. And what's even more is I know that if I have examples of something that satisfies those rules that's not trivial, then I know that that free thing will be not trivial also. Then you know, there's some general way of doing this. I might not be able to describe it easily, but I'll know that there is one. And that's very encouraging because at the outset you might not be able to know that there is a general way of doing this at all. Okay, so it looks like what I want. Okay, so I can't, okay, so I looks like what I want is, I want an endless sequence of operations. Okay, I see. So, okay, so here's the revised what it is that I want. And actually, you know, I'm really glad that I have a recording of this too, just because like this is me actually just kind of, I mean, it's not like maybe a serious research interest necessarily, but this is like a thing that I've been meaning to think about. It was a, pet project when I was younger, and you're really getting to see my process of how, like, often when I describe how I solve problems to people, I mean, there's no one right way to do this. Everyone has, like, different ways that they do these things. But when I describe the process that I use to people, I'll often say, like, I decide, like, when I have, like, a problem I'm trying to solve, or when I'm doing math, I'll say, like, it's not like someone just shows up to me, usually, I mean, it depends on the situation, but usually someone doesn't just show up to me and say, like, I have this problem, here's this big famous problem, I want you to solve the problem. Like, and then, I try to solve the problem. Like, that's not my normal experience of life. My normal experience of life is saying, like, it would be really cool if there was some kind of algebraic structure, some kind of geometric construction, some kind of system that did this thing. I think that would be cool. I want there to be such a thing. And then I describe in increasing amounts of detail what that thing would be. And at some point, I either conclude that there is no such thing, or I manage to manufacture, usually not just one, but an endless, family of them with, all various relationships with each other. And so, I'll often just say to people, like, I decide what I want, and then either I can have it or I can't have it, like, either it exists or it doesn't. And, like, this is that process where I just iteratively say, oh, I can't have that because those things don't go together. And then I'll say, okay, but what I really wanted was this. And that's much more my experience of usually doing math. It's just an endless series of me saying, I would like this, can I have it? And then the, universe or whatever comes back and says, no, you can't have that one. We're like, okay, but can I have this? And we're like, oh, all right, I guess so, but, and, like, that's what it's like to me, Like, different people have, like, different metaphors or different, like, intuitive ways that they think of doing this, for some people it's weightlifting, or, some people it's other things, but, like, for me it's just like, oh, I'd really like this, and then I can either have it or I can't, and then I ask for something else, and I just keep doing that forever. For textbook problems, so it depends on the problem. So, like, what I just described is more exploratory, and so it's maybe more in the vein of, like, a lot of the, like, more, like, category theory or, like, algebra people are a lot more, like, into, like, the the Grothendieck story about, like, the rising sea, that, like, his artsy metaphor was that, like, the sea, like, weathers down like a walnut, and then, like, it just opens up by itself one day. And that's kind of like this idea of, like, I'll just keep exploring things that are similar to what I want, and then eventually I will understand. Like, things will come out, and then I will understand. And that's basically the process of repeatedly, like, saying, like, can I make something like this? And either you can, or you find it's impossible, or you just fail and try something else because you couldn't figure it out. And so you can learn that way. It is a lot more, like, sort of meandering. Like, it can be slower, but eventually, if you really still put, like, dedication and effort into it, it will yield, like, tons of results. Things will be obvious to you that aren't obvious to other people. But for solving a specific problem, like in Grothendieck's metaphor, the other way to open a walnut, besides just leaving it on the beach for the ocean to weather it away, is to just, like, smash it with a hammer until it's smashed open, and then you, like, pick out the little pieces. And so for the people who like to, like, just choose a specific problem and just attack it, like, really really hard, it's a common metaphor that people have heard. That's more this technique of, like, just keeping this bag of, like, problem solving tricks and trying the tricks over and over and over and over again, until it works, or until you give up, and so I guess as far as applying the attitude to textbook problems, or just problems in math in general, I guess I would say that if my goal, instead of just having a general overarching understanding of an area or a type of mathematical structure or something like that, I guess I would say that if you have a specific problem that you really want to solve, and especially textbook problems are kind of easier in the sense that you know that oh, well, okay, you don't know for sure, but assuming the problem's not wrong, you know that there is a way to solve it using things you've already seen in the textbook section. So like, you know, you've got a leg up there. But I would say that this most resembles the technique of when you're given a problem, you write down everything that you're given, like, in the problem, and, like, you figure out everything that you can easily conclude from that. Like, everything that's, like, immediately, right. They're textbook problems are like, yeah, if you're going to try to do the metaphor with those, it's that, maybe that the walnut is very close to being opened already. It's been weathered down already, so you just have to do it a little bit. Your immediate exploration of the consequences of whatever, you know, the textbook problems say, suppose this, and this. Your initial task should be, what things can I obviously conclude from all of this information? And just start accumulating an increasingly large list of all the things that you can conclude that seem interesting to you or relevant to the topic at hand. Now, of course, one thing that makes, you know, math difficult to automate is that there's, in reality, a quite unlimited amount of such things, but some of them will just kind of speak out to you more as you get more experience, and you'll write down those, or you'll say, I think that this has to do with the theme or the topic of the textbook section. And if you write down enough of that information, and maybe try to come up with some examples, if it'll say, like, consider, you know, a function that's, you know, increasing over these intervals and whose integral is bounded by this quantity, you know, if you start trying to come up with examples of such a function, examples of such a thing, and figuring out what sort of maybe more obvious properties it will have, eventually your combination of examples and properties that you can easily prove will usually unravel into the desired proof. Like, that's basically what a lot of textbook questions are like, is like, I used the techniques here to produce this insight, and you know that can be done through a sequence of such steps. So just start doing those steps more or less randomly, but maybe using your intuition to guide you, and eventually you will have the solution. So, I mean, maybe that's what the more direct problem solvers would say too, or that's some version of it. Maybe we all just do substantially the same thing, but we have different metaphors that guide us. I don't know, you know. But anyway, that's how I would think about it. Is like that. And for what it's worth, I actually find, you know, I've solved a lot of textbook exercises in my time, and I find that doing textbook exercises is like, it's easier. I mean, they're easier than answering a lot of questions in research, but they're also like, there's also like an added difficulty, which is that textbook questions have a little bit of an aspect of like finish the pattern that I've complained about before, where it's like, there are an infinite number of directions you can go off in, and if someone tells you they were able to reach this particular place starting at the same starting point, as long as it's reasonably doable, then you will be able to figure out how to do it. Some people will do it faster than others, but like, you know, whatever, right? But it's a little unnatural in the sense that they're guiding you towards the things that they found or the things that they think are instructive for you to find, but that might not be what's obvious to you. Two people presented with like the same like basic setup and the same like initial like results and everything will go off in two different directions, like naturally on their own interest, and like neither one of those people is correct. You know, like there's not one right way to do it. It just happens that some people will, you know, explore in one direction as opposed to another. And so, you know, textbooks are always kind of artificial in the sense that like you're trying to give someone an intro to the area, but like even once you're halfway through some intro algebra book, some people's interests are going to be totally diverging from others, and what's obvious to some people will become like totally different depending on the student. So it's actually a pretty tough thing to, you know, come up with good exercises that are helpful and instructive to everyone and that are reasonably doable. It gets harder and harder as time goes on and people split apart into different areas. Anyway, kind of ranting a little bit, but yeah, I guess that's my take. Um, but oh yeah, so as far as yeah, um, you yeah, so you just do the homework wrong and then you read the professor's solutions. Um, oh, I'm glad that was helpful. Uh, yeah, yeah. So I mean, it's anything you figure out. Okay, this is the other thing, and I've said it before, and I'll keep saying it again. I'm sure I'm not the first person to say this. Also, you really, aside from doing the homework, like you've got to try to come up with your own stuff, even if it's bad, even if it's not interesting. Like anything that you figure out on your own without anyone asking you to do it, just a cool thing that you notice on your own that no one asked you to do, that's worth so much more than doing a bunch of exercises, because you did the actual process of advancing that topic. Now, you might not have proved a brand new theorem that everyone's going to be excited about that you can publish, but that's you, for your own mental model of this thing, you've pushed the boundary and like you've added to it, and like that experience is the experience of doing mathematics. Like that's what it is to really create new math. Yeah, so this is the other thing about math, that like depending on how hard people are gatekeeping you about it, the reality is that sometimes things are just a trick, and if you use a trick enough, you can call it a technique. And a big part of, especially if you see like young people who haven't had like, many university classes or much experience, a lot of being good at math is literally just having accumulated many of these tricks prior to your peers, because you were somehow or other interested in or instructed in these particular things, and then you can just like be like, oh well, obviously whatever, and blow people away. But a lot of these aren't necessarily because you figured it out, it's just because somebody already told you. And so yeah, unfortunately, there's not really like a general repository. I mean, you can look at math problem solving books, Olympiad books, whatever, but like the reality is just that there's an endless amount of such things, such like little tricks or techniques, and all you can do is try to accumulate a critical mass of them until people respond to you by saying, yep, that's definitely a mathematician, that's someone who does math. Like that's I wish I could give a better answer for that one, but like yeah. Yeah. Yeah, like it's it's definitely the case. I want to say, as far as the comment about giving experts something and they say this is interesting, I'll think about it. Like, you know, there is no point at which you will be able to like instantaneously or otherwise like solve all Olympiad style. Like, I'm not super into doing Olympiads, but just to give you the example of like the most problem solving-y kind of problem solving things that people do as contests. There's no point at which you can reasonably expect to be able to like instantaneously do all of these problems, especially if you're going to be a research mathematician. Like, that's not your job, and that's not like what you're probably going to realistically spend your time doing, unless you're coaching a team, and even then they may get stuff faster than you. Even it's possible. It's like there was some big one that in like the IMO or something, where like they brought in a bunch of like number theorists to like grade the the question, and like it was a number theory question. I've seen the question before. I don't remember what it is now, but like they like a bunch of experts like couldn't produce the answer to this question, but like these high schoolers who had been trained, or maybe college students, I don't remember, who had been trained in like the specific relevant technique or problem solving tricks that appear on all those problems, did it. Like, I mean, maybe not all of them, but some of them did it, and they did it correctly. And it's like, that doesn't mean that they're better at number theory than the number theorists. It's just it's there's some aspect of it that's just like a kind of a mechanical, like you can learn the tricks and then you do the tricks and then you can solve all problems that reasonably use the tricks. But yeah, it's so don't get too down on yourself if you're not the fastest or whatever. And you'll also hear a lot of people who do research will say like, I don't solve textbook problems anymore, or it's very rare. I might write problems, but I don't really solve them very much. And what was the other thing I was going to say? Just that, yeah, like it's something that tends, you eventually kind of, I wouldn't say you grow out of it like forever, but like, people don't just sit around solving textbook problems forever. I still like doing it, by the way. Like, it's something that I like to do, but if I go to try to do that now, unless I really need to learn like a new area and more depth, I usually I might read the textbook problems, and if one is really relevant or interesting, usually I'll be like, oh, that's a good result, or that's a good technique, I'll use that. But I usually don't grind through all the textbook problems and anything anymore, because I'm like, I shouldn't really spend my time like that. I should be writing a paper, or doing something else like that. I should be doing my research. Yeah, I mean, not that it's wrong to keep learning, keep working on textbooks, but it's just I also find that when I learn new things by using them or experimenting with them. Doing textbook exercises, it has a limited utility in me learning quickly now, but that's probably because I've done so many textbook exercises before. But yeah, I mean, this is all just my opinion. This is my experience. Your mileage may vary. I don't know. But yeah, thanks for the awesome questions. I feel like I'm kind of trailing off as far as the problem solving stuff. But yeah, before talking about this too, I never really thought about so there are these different metaphors, but as far as what they actually result in, the different things that they result in materially. I'm starting to wonder if we just kind of I don't know, we tell ourselves that we're very different, that algebraists are very different from analysts or something, but we really just have different metaphors for doing the same exact thing. Yeah. I can't relate as much to the it's tough when you can't use something or play with it very well because you're still at such a basic level, because my experience in life just happened to be that I was very predisposed to I was just very predisposed to mess around with stuff even when I really didn't know as much as I needed to do something interesting. And so the first stuff wasn't great, it's like writing a song for the first time or something, right? It's and despite people's mythologies, it's really not everyone starts somewhere. It's really not you're not going to just pick up the instrument and be proficient at it, but yeah, I mean, I definitely encourage experimenting as soon as possible. Oh, good. I'm actually not very musical myself, so I'm glad that my musical analogy worked the way it was supposed to. Thank you. But yeah. Oh yeah. I did when I was younger. I will admit I messed around with Fruity Loops just a little bit, but it's been a very long time, and I didn't produce anything I think of any particular value. I mean, it's a balance, right? You should expose, yourself to other people's textbooks, to other people's stuff that they've tried, to get, an impression and everything of what they do. But yeah, it's just, I know it feels like, it might feel like it's pointless, or it's there's too much time. Maybe not that it's hopeless, but that it's so time consuming. But it's kind of to keep on with the art or music analogy. It's you can learn the technical skills forever. You can keep training on doing your scales, knowing your various color theory things and everything. But until you decide I want to write a song about about the spring, I want to paint a mountain, until you have a thing that you want to do with it, it's just you're not yeah, you're not going to learn how to do it. Yeah, and that also, the unfortunate flip side of this is that people who mindlessly amass including just blatantly memorizing Wikipedia pages and stuff, people who just blindly amass certain technical things, knowing how to recite that like, a monad is a monoid in a category of endofunctors. Like people who just, people just use these things like mantras to be like, I'm smart and like therefore I know it, and like, like you don't know it, right? But like, knowing that's, memorizing or like, consuming that stuff is very different from actually creating mathematics. Yeah, I'm really glad that that this analogy is so good. It's like, yeah, like, I mean, to the extent that I've proven anything here today so far, like, what have I realized? I realized that, like, somewhere back here, I realized that, like, I looked at a bunch of cases of this thing, right? This construction that I was interested in. I looked at a bunch of cases, and at some point, I realized that, like, well, I can't have unique solutions, and like the proof, I think I didn't even keep it, I just deleted it. Like, it was like, if I have a ring sitting inside there, I mean, you can't have this, because this has infinitely many solutions, so it's a pretty trivial proof. But like, I really feel like the most like mathematical substance was me starting to think, okay, maybe I need to artificially split apart the not well-defined division into an endless amount of well-defined division type operations. That's like an actual idea. Like, that's like not necessarily the best idea in the world. Like, it's just an idea that might be helpful. But like, that was an actual idea that I had, and you watched me have it. I didn't plan this out, and I didn't sit there and try to come up with it like beforehand. I really didn't. I just said I wanted to think about this construction more, and then I thought, maybe I can cheat, and like the way I cheated might actually be like a good thing to do. I mean, we'll have to see what the consequences are, but that's actually what it's like, It's not like occasionally, like, you can pull out, like, there's a really useful theorem. In fact, I'm trying to do this so that I can use, like, the existence of free algebras in varieties. Like, it's like, occasionally, like, there will be like a big theorem that you just pull out and you're like, yeah, like, I can use this theorem, and then I solved it, or I made it, or whatever. But there's a lot of times when it's just having an idea, like, oh, can I get away with something? Can I change this in a way that makes it easier? Like, yeah. Oh, yeah. Yeah, exactly. Like, you do need some background. I mean, to make something that's maybe of a higher quality, you can start trying to make your own song at any time, right? Kids take pots and pans and just start smashing them, and are like, yeah, this sounds great. I'm famous, whatever. But and it's important to do with math too. Just start making stuff, even if it's not the best stuff at first. I mean, but it'll be cool and it'll be fun and everything, or at least it is for me. You start making stuff, and eventually you get enough of that technical background that you can make like cool stuff. That'll be a great T-shirt. I'm famous, like, child, like, smashing on a pot. Yeah, like, yeah. I mean, that's what it is to be a rock star, I suppose. Like, thanks. Yeah, thanks again. I'm always glad to have such good discussion. It's part of what makes this really fun. Yeah. Yeah, the nice thing about math is that if there's any danger, the danger is usually that other people will do something questionable with the knowledge or algorithm that you've generated. It's very rare. I mean, I think, as I've illustrated here, hopefully today, it's very rare that you actually cause like some kind of like failure in the structure of reality or anything like that. As you can see, I've been messing around with dividing by zero for some time now, and there have not been any explosions or wormholes of any kind. Now, that could just be because those versions of reality that were less stable to it, were destroyed by me trying to divide by zero. But at least in whatever one we currently find ourselves in, this seems to be fine. So as long as you're careful, you shouldn't create any kind of wormholes or anything like that. Because it's just math, it's not, you're not messing around with a particle accelerator or something. Um, but yeah, I mean, if something does explode, you should definitely warn people about it. Although I guess if you had to tell them what the math was that did it, then maybe it would just make the explosion again. I feel like there's a science fiction story in here somewhere. I'm not really sure exactly, but something like that. Okay. Oh yes. Thank you. Yeah, I believe it or not, when I was younger, I did actually type up some proofs of things in Microsoft Word using the equation editor, and it was brutal. So, yes, by all means, if you if you if you do that, you can just send it right off to me. You can just send me a letter at if you send it to the math department at CU Boulder, then I'll get it. Don't send me anything dangerous though. But yeah, I mean, like if your theorem has any dangerous safety implications, don't maybe not that, but like anything reasonable, I'll definitely be happy to read. Yeah, mathematicians have a bad history with things being sent in the mail, so yeah. Oh, nothing but angle trisections. Okay, this is the traditional stuff that's totally safe, yeah. Like you can, sorry, I dropped my water bottle here. You can just send me all the angle trisections that you want. Yeah, yeah, this is a fun thing to think about. The whole Western kind of fantasy style with wizards and witches and all that. I mean, it's based on I think a couple real sources. And so one of those is traditional religion in Europe, traditional like Wicca, that kind of thing. But the other one is Western academia, which has existed for at least 1,000 years, in a similar style to now, with the robes and the fancy towers and so forth. And so it's actually not a coincidence that that stuff resembles academic regalia and academic culture and that sort of thing. And they're wizened old wizards who have these books full of arcane symbols and maybe different languages and so forth. And it's actually not a coincidence, and it's pretty wild to think about the fact that mathematics is this arcane symbolic language that you have all of these tomes for, and knowledge of this somehow allows us to create various things using knowledge of chemistry, physics, biology to create and affect things in the world that can produce effects that are fantastical, but of course we call it science and not magic or witchcraft or something. But I mean, I call what I do witchcraft on a regular basis, in a somewhat humorous way. But yeah, I mean, it's actually the real world version of having an arcane tome with symbols and diagrams that helps you to somehow alter the shape of reality. That's math and its relationship with the scientific process. That's basically what it is. We just don't find it fantastical because it's our everyday lives. But I mean, that's what it is. You have some kind of screen in front of you that's transmitting in real time or close to real time. Whatever it is that I'm saying and doing here, and my arcane symbols that I'm doing and everything. You're experiencing it right now. Yeah, it's basically math research and magic research are basically, that's what it's like. It's I mean, it's helpful to romanticize your life, but in this case I really think art imitates life, and the reason why there are so many depictions of magical people like this is that there's been some kind of synthesis between traditional religious practices related to magic and academic culture in the West especially, which has it's there's no coincidence that the way that what you think of when you think of a fantasy wizard and what you think of when you think of academic regalia or similar, it's intentional. That's where I'm quite sure that's where it came from. Yeah. I mean, yeah, I don't know. It's a fun thing. Yes, we're magic. This is all very magical. Oh, I've seen the covers of those. I've seen pictures of that. The manga guides to calculus and linear algebra. I have no idea if they're any good or not, but yeah, I've seen that. I prefer to just imagine the magical implications of these things. You know, I don't really need it to actually be explicitly instantiated in the textbooks, but if it helps someone, then more power to you. Yeah. So as far as this goes, with this division, these cheating divisions that I have, I was thinking that I want maybe one of these divisions for each like for each integer or something. Oh, okay. What about this? What about this? Maybe this is what I want. I want to see if I can describe the kind of algebraic structure that I'm looking for. So what do I want to do? I want to fix a ring R, which has its addition, subtraction, multiplication, 0 and 1. All right. Okay. So consider an algebra. So I want A to be something where it has addition, subtraction, multiplication, 0, 1, and then it also has a sequence of other operations, which are these division, like these S division operations, for each S in the ring R. Okay, so where? Okay, so then the question is where what has to happen? So I guess I want that this. I guess I want that this is a ring. So this is the most natural thing to ask for, I guess. Where this is a ring. No, I can't have that. Sorry, I just realized. That's not possible. That's not possible. Okay. The reason it's not possible is to keep you along with me here. I know that the multiplication can't be associative because if there's something that is a solution to this is what I was trying to write down before when I realized I actually had just a direct contradiction. If I have something that does this, then if I do 0 alpha, 0 times 1 is 0. But if I do this, right? So this can't be associative. So I can't ask that that's a ring. I can't complete the ring to something that has all of that has like division by 0 in this way and still have that this is a ring. But I don't know of any other ring properties that are violated by having these elements that are like 1 over 0. So what I might ask is that, let's see, can we make it so that this is a non-associative ring, maybe? I don't know, maybe that. And what else do we want? We want a non-associative ring. In other words, it's like a ring, but the multiplication's not associative. No. All right, well. Oh, that was actually pretty good. Nice. Okay. And something else. What is the something else? So where that's a non-associative ring, and well, this division is supposed to work the way that we intended. So x times, so that has to be equal to, well, okay, so there's two possibilities though. It's going to be y, it's going to be like, okay, well here it'd be x when x and y are not both 0, but it would be s otherwise. So I want this to work the way that it is supposed to, but what is that? I want to say that this solves the appropriate equation. But if I say that that equals y, what is this gonna mean? Either x and y are both 0. Either x and y are both 0, in which case this should be giving me s, which might not be 0. So that would make it have to be s in that case. I thought that this cheat was going to work, but now I'm not feeling so confident anymore. Because I want to be able to represent the behavior of this as an equation, but I'm starting to realize that I still have the problem of these cases. So I'm saying if x equals y equals 0, so and I guess what I can do equationally is I can force that 0 times 0 s 0 is equal to s. I can demand that that's true. But for the other one, I can't. So I feel like I'd like a formula instead. Because this is like saying 0 times 3 is 0. So when I say, so I'm saying like 3 is like 0 over 0, but in the 3 way. In the 3 sense, you know? So if I had some other things I was dividing, like, you know, well, if I said like, okay, 6 times something is 18, well, I know there's only one solution, right? It's 18 divided by 6, which is 3. But maybe what I can do instead is just say something like, well, this is maybe this is this, or this is just this for any choice of s. Maybe it just happens to be that they all give me 3. And so then okay, so I would be saying instead something like okay, so I'm saying something slightly different from this. I'm saying that I want this weird division. When you're doing this with zeros, like 0 over 0, this is saying like, oh yeah, I want the solution that is wait. That to be like 3. Oh, I was just saying this in a way that didn't actually make sense before. That was the problem. Okay, so I'm saying here that like 0 divided by 0 in like the 3 way, in the 3 sense, is like the solution that is 3. That's that solution, but this is a different solution. So I'm just basically allowing an infinite like family of solutions to these problems. But I should do it for not just 0 and 0, but for anything and anything else. But in those cases, there will just be a natural single answer for that. But in any case, what I am saying is actually, if I do this correctly in a way that makes sense, what I'm really saying is that if I if I do x divided by y, and it's supposed to be the s result of that, then if I multiply by y, then I should just get, no, I should get s. No. Yeah, I can't get this. This isn't solving the problem of it being well defined. Because the problem is, like, I want to split it for 0, but I want to have an equation that tells me how this always works. But there's two possibilities. One is that, yeah, I see. There's two possibilities. One is that x and y are both 0, which is what I meant when I was discussing this first case. One is that x and y are both 0, in which case I want this to just give me s. But the other one is that x and y are not both 0, in which case I should get whatever the relevant division is, regardless of the value of s. So I always want, but then what I'm saying is I always want this to solve the equation that y times this is equal to x. Okay. So I'm saying I always want that to solve that equation. Does that make sense in the different cases? Am I just getting caught up in this for no reason? So here I'd be saying 6 times whatever the thing that's 18 s divided by y is 18. So that should be a solution, not y, but 6. That should be a solution to the equation 6 times something equals 18. All right, fine. I can just define that to be 3 for all of those. On the other hand, if I had 0 times 0 s divided by 0, I want that to be 0. Oh, no, but that makes, okay, I see, that makes sense. So this is like just like saying, like, I can have an infinite number of solutions. Okay, no, I'm actually okay with this. I think that this is okay. I think I was messing with myself. I just need this to be true. The only function that this has is it basically allows me to have just like an arbitrary family of division operations that all do the same thing for every pair of things except for, how do I want to say this? I think that this works, is what I'm trying to say. So, in other words, this kind of cheat allows me to define a system, like in principle I should be able to have a system where I say, okay, 0 s divided by 0 is just s. That's that solution s to this equation. But then if I'm given one that's like 18 s divided by 6, I'll just make it be 3 for all values of s. And so it's at least conceivable that I could have such a thing. So I think this is what I want. The reason why I was so concerned with getting an equation like this is because I don't know whether there are I'm not sure whether there are non-trivial examples of this yet, where this is a non-associative ring. But what I just asked for here, this is a description of a variety of algebras in the sense of universal algebra, because this has a family of basic operations that are finitary operations, and there are an endless family perhaps if the ring R is infinite, but that's okay. And this is all of the properties of being a non-associative ring, and these are universally quantified equations. And so because of that, this is a variety of algebras. There is a free, like, most general thing of this that is like somewhat analogous to the role that like the integers play in groups, for instance. It's like the free group on a single generator. There are free things like this. The question is, are they trivial? Or in other words, can I actually get the non-associative, at least part of the ring structure, with something that does this? And that's a question which I definitely don't think I'll be able to answer in the next few minutes. But at least that's a good thing to investigate. And so this also is fitting along with like the pedagogical, like expository nature of the article that I've been thinking about, because what I'm saying here is like here's I don't know how hard it is. It may or may not be an exercise, but like here's something to consider now. Like this defines a variety of algebras, like groups or rings or other such things, modules over a fixed ring. So the question is it the trivial variety? Are the only examples of this trivial? Or is it possible to have something like this that's, well, okay, I guess I should say yes, it's possible. No, maybe not. I thought I had a not trivial but easy example, and I realized I didn't. The problem is the zero divisions, right? Like anything that looks like this is going to have something that acts like dividing by zero, for sure. And so the question is basically, can you do addition in a way that is compatible with the multiplication? Oh, I think I'm starting to see it. I think that this exists. I'm hopeful anyway. I'm starting to feel like this exists, because I'm starting to think that I can understand what the free thing is supposed to look like, maybe. Okay, so here's my guess. I'm not going to have time to like fully prove this or flesh it out, but I'm going to give you my guess, and it's the following thing. Okay, so of course I don't want to make my life any harder than it has to be, so I'm going to take my ring R to be the integers, because I don't want to have to do any more work than that. So if I had the integers, then my algebraic structure would have to contain if I had a non-trivial example, say that contained the integers, so I had an example of an algebraic structure like this, I'd be able to form things like 1 s divided for whatever s by 0. That would be a solution to 0 times this thing is equal to 1. So all things like this would play the role of 1 divided by 0. Maybe there's more than 1, whatever, let's not worry about it. So these would play the role of like 1 divided by 0. And so I'd have things like this. And then, I'd want to be able to divide those by 0 as well, so I'd have to have things that were solutions to 0 times something would be 1 s divided by 0, so that would be like 1, maybe I'll say t divided. No, that looks too much like a plus sign. Say s prime. S prime divided by 0. Oh no, I wanted s divided by 0. 1 s divided by 0, s prime divided by 0 is equal to 1 s divided by 0. Okay, so that's a thing that I have to have. In other words, this is the solution to taking that thing and dividing it by 0 again. It's like dividing by 0 twice, but the first time it's like the s way of dividing by 0, and the second way it's the s prime way of dividing by 0. And because I'm trying to do this in the most general way possible, I'm not going to declare whether those are the same or not. I don't care. So I can form all such things like this. All right. Well, I need to understand how that interacts with the ring operations. If I'm to have a non-associative ring, I know the multiplication can't be associative, but I might still have that there's an additive group structure, and that the ring operations distribute over the group operations. So one way to test this is to say, if I do 0 times x plus y, even in a non-associative ring, I should get 0 times x plus 0 times y. And I should also be able to conclude then that if I do 0 times x plus its additive inverse, like negative x, or I guess well, whatever, I'll just leave it there. Then I should be able to get 0x plus 0 times negative x, but that should also be the same thing as 0 times 0. So I should be able to get that, for instance. Oh, I think that this looks like this is still okay, because like if I do 0 times, and now just for laziness, like there should be an element that's like 1 over 0. It's like the s division of 1 by 0. I'm just not going to write the s. And there should be something that is its additive inverse, which I will just write as negative 1 over 0 and not really think about whether that has to be negative 1 over 0 at the moment. Let's just not worry. But it has it should have an additive inverse. That must exist if I were to have such an algebraic structure. Okay, but then if I did have distributivity, then this should be the same thing as 0 times 1 over 0 plus 0 times negative 1 over 0. And so if I did have this, if I did have this, then this would be saying 1 plus 0 times negative 1 over 0. And then on the other hand, over here, we would have 0 times 0. Let's see. And so even in a non-associative ring, I think I should be able to still have that 0 times 0 is 0. And so if that's true, then that should mean that that's negative 1. I'm not finding like an obvious contradiction that I can produce. So I think what's going to end up happening is that a typical element of one of these things is going to look like you could have like maybe 1 like s divided by 0, plus like 3 s prime divided by 0 plus like 7 s divided, or maybe s double prime divided by 0, s triple prime divided by 0. Like this is like you're gonna have like just a whole bunch of things like this, and so additively you're gonna end up with you're gonna end up with something that is spanned by a bunch of guys that look like this. So like, I guess the question is, can I prove that like if I have like 1 s divided by 0 and I add it to 1 s divided by 0, can I prove that that is equal to 2 s divided by 0, or is that not a thing? Well, I guess if I multiply the left-hand side, I see. Just, multiplying both sides by 0 and distributing, I would get the same thing. But that doesn't really prove that they have to be equal. That's compatible, but that doesn't necessarily have to be the case, maybe. Alright. Well, anyway, I told you I wouldn't be able to completely flesh it out in this amount of time, but at least at the moment, I haven't actually proven to you that this is a non-trivial variety of algebras, but I also haven't found any contradiction that I've immediately seen that seems like there can't exist something like this. So I'm thinking that this may work. Yeah, it gets dark so fast. Yeah, the sun is set. Now you can see me. You can see my new place with the plants and so forth behind me. yeah, it's been really cool again. I hope that you didn't lose faith in me last week. I was just straining to carry heavy things, upstairs and so forth. So you know. But I did finally get my whole setup back again, and there should be the nice twinkle lights will be back here soon, and it'll be very pretty and everything. Yeah, thanks so much for joining me on this adventure again. As I thank you. Thanks for joining me here again. As I continue to mess around with division by zero. I felt really good about this one. I'm really happy that you were able to watch me. Maybe possibly figure some things out, or at least make some good progress. And thanks again for all the awesome questions and comments and conversation. It's really what makes this fun. The balance between watching me fiddle around with whatever it is and asking for advice and stuff. I guess I'm still a few minutes early technically, but it maybe seems like a good place to wrap up. So I'll just say bye everyone, and thanks so much again. I'm really looking forward to it next week too, and I'll definitely be in touch. As I mentioned, I'll be going to Asia at some point as well. So I'll figure out what I'm doing during that time, but I will definitely have something for you at this time slot for sure. Whether it's live or not, I don't know, but I will figure it out. All right, well, thanks so much, everyone, again, and have a wonderful rest of your day or night or whatever it is, when and wherever it is that you are in the universe at the moment. Well, thank you all so much. Have a great time. See you next time. Bye.